like classification. At the same time, deep learning also you can also perform classification. Good, yeah. So deep learning, there's no feature engineering task where the first half machine learning you have to pre-process the data, then followed by next half we use some machine learning algorithm for classification. Whereas the deep learning neural network we have a lot of layers, right? The feature engineering itself maybe the initial layers if you perform first the feature engineering like extracting of features, maybe low level features, mid level features, and so on, then followed by next level. So which is classification. So and then what is this generative AI? What kind of data we can generate? How it generates the data? So it can generate text data, right? It can generate image, video, voice, right? It can generate all kinds of data. But how? So what is the operation? No methodology behind that. How it generates data? So it is trained on huge amount of data, billions of records. I can say, and I can say billions of parameters required, right? We see coming slides how many parameters required that. I can say ChatGPT or version 1, 2, 3 billions of I think I guess few billions of books, web pages, and then a lot of resources, databases they use for training the basic generative models like GPT and BET. Okay. So some of the major players in this, see this one, Google, everybody knows, or Alphabet, Meta, Facebook. So which models they release, like Llama by Meta, Facebook, and Nvidia is one of the active players, OpenAI, Microsoft, and this company is a new one, Anthropic. So it is this startup started in 2023, but they produce a lot of models, very good models. Okay. Yeah. Okay. Then we have NLP, natural language processing. What is this NLP? So NLP, how many languages we have? Like throughout the world, maybe 1,000, 2,000, 5,000 languages, different languages are there. But how machine really understand the context is different, Telugu or Kannada, Hindi, English, completely different, right? Script is different, the way, words and relations, completely different. So, but how a machine can understand? Like, that's what. In natural language processing, we have some text, some language, a lot of, I can say, 100 lines, 200 lines, 500 lines. So, it needs to understand the linguistics, right? So, for that, we are going to use computer algorithms. So, we have a lot of algorithms, okay, pre-processing tasks followed by a lot of algorithms, again, to understand the human language. So, that's what natural languages, right? Similarly, security, cyber security with we're saying generative AI. So how we can use like for GPT, we are saying when you give some prompt, say for example, I just want to know about Malla Engineering College. So you want to like generally earlier we used to search in Google. Now you have GPT. ChatGPT also you can search, right? You can search. I have just generated about for this session small prompt. So I just want to know about Malla Engineering College. So it has described, I have given the token length as 500. It has generated some text. I used just a free open source model and I generated 500 words about the college. Okay. So obviously it has to be trained. Millions of parameters are required. Okay. So I just want to say generative AI in cybersecurity. For example, if I say generative AI in cybersecurity, so we have SOC. What is this? Security Operations Center. Every company maintains this Security Operations Center, followed by Security Event and Incident Management (SEAM). Okay, so that is also essential. As I told you earlier, many companies have their own, centers to solve cyber threats and cyber security issues. Okay, they are maintaining this at the cost, look, the highest, like, they are spending a lot of money on this, but still there are a lot of issues. So how we can do that? Like, what kind of issues? Cyber threats, malware, ransomware, and so on. So how generative AI can be used? So we are going to, I'll discuss a paper, recent research paper for 24 people. Uh, See, they have used bent model, okay, so which is next to the transformer model. We'll discuss transformer and bent as well as GPT architecture as well. So how they use in a sophisticated way to perform lot of threats, like I can say 14 threats they could identify and predict, okay, with some 97-98% accuracy. So from the data they have used IoT data, which is a standard data set, and how we can use, like, predict that kind of threats using large language models. So initially we study, like, we understand what is large language model, that is transformer based model, then how we can use these architectures for this stuff like cybersecurity threats. Okay. Okay. So image generation and all. So because of time constraint, everybody knows. If I give a prompt like painting of a flying dog, it generates something. It's next. Similarly, text also, as I told you, we see some examples with some lightweight model, how we can generate prompts also. Okay, chat GPT, next one. So everybody knows GPT, generative pre-trained transformer. So this transformer is a breakthrough in artificial intelligence. How many of you heard about transformers? Please raise your hand. Just one. Okay, good. So we'll be seeing the architecture of transformer, then a bed model. If you understand transformer model, generative AI you can easily understand. Okay. So how chat GPT or large language models like GPT, you know, is designed and still they are updating version by version. Okay. The first vast amounts of data is required, which is training data. So supervised, is it supervised learning or unsupervised learning? Let's say supervised learning, right? We need vast amount of data to train. So vast amount, just now I told you, hundreds of textbooks, okay, web resources, databases, they train, okay, to design one large language model. Then transform data into tokens. So when, like, see this one, 500 billion tokens, just imagine, okay, how many parameters, right? And yeah, so we need billions of like I can say words to train for a particular model. Second thing, sometimes we need unsupervised training. Why? Because uh, every time we can't say, you can't expect always I have only labeled it, right? Sometimes the data may be unlabeled also. So that time, obviously, you have to go with unsupervised learning, okay? And then fine tuning. So I have a pre-trained model, so which is used for general tasks. Then maybe I want to use that particular general model for specific to my task. Yes, I can use that model. But what is required? Say I have a general model. Now, I just want to fine tune that for my application. For example, in a banking application or maybe iPod or on application purpose, I just want to train that model or fine tune the model. So that is compared to it is very less cost, right? So we have a base model. On top of that, limited data, adding few layers. I'm fine tuning my model with the given data. That is what fine tuning is. Okay. So I hope it's clear. I have a model, for example, I have a respect model or a transfer model. On top of that, I add few layers specific to my data, specific to my data, my application. The problem can be anything, banking application, education, industry, whatever it is. Okay. So with few layers, limited data, so I can train my model. That's how I find tune. Okay. And then reinforcement learning. Say it generates something, but generated thing, a classified thing is correct or not, that we have to assess. Some feedback is required for the machine. That's what reinforcement learning is. Reinforcement learning. So human reviews that prompt or whatever the response is. It after receiving that response, whether it is correct or not, you're going to give feedback. So it's a good, bad, average, something like that. So based on that, it learns, okay, this prompt is correct, like this prompt, for this prompt, the response is correct. So that way it learns, and next time it generates a similar content, maybe with additional data. So that's what this RLHF is, reinforcement learning with human feedback. So that's how this new versions of GPT 3.54, maybe this month, it is expected that GPT 5 will be released. Okay, with again billions of parameters, maybe it may go up to trillions of parameters. I think it's not parameters, tokens. Okay. Yeah. Okay, so for training, we need vast amount of data and then transform data into tokens. So machine don't know. So when I say word, I love cricket, for example, they don't know what is the word I love, whatever it is, right? Or in Hindi, if you say some sentence, you don't know. So obviously, you have to translate that into a machine understandable language. So initially, we have a text maybe in one language. Okay, so you have to divide, like I can say, process the data, that means divide that into tokens. Okay. Then followed by unsupervised learning. Sometimes you may, since it is a huge amount of data, you need unsupervised learning as well. Sometimes. Okay. Then fine tune that model. Then use apply this the reinforcement learning with some feedback and deploy it. This is how generally large language models are developed and improved. Okay. So you can see the training data for GPT-3. Yeah, 2018 GPT-1 was released, GPT-2, GPT-3, next consecutive years, and then the remaining years 2021. DALI. I don't know how many of you used generative adversarial networks. That is DALI, and then 2022 Instruct GPT, then Chat GPT in 2022, 23 consecutively. So March 2024 GPT-4. Okay. So yeah. So how you can improve LLMs? See, one thing is whatever the model you have, as I told you, the base model, developing from scratch is difficult. Okay, I can show you this. You can understand. See, on top it is easy and cheap, whereas bottom difficult and expensive. So see this one. If you want to train your own model, like you want to design a model and you want to train from scratch your data, complete data, then it is very expensive and it takes a lot of time, right? I have a model, okay, some XYZ model I developed, my algorithm. Now I have data, okay, how to train, okay. Say, for example, if we take 2000, 5000 images, for example, image data, or some 1 billion words, for example, in text. So if you design your own algorithm, obviously it takes a lot of time and not only time, computational power also. You see, with your Colab, Colab Pro, so for 1 hour this week, daily 1 hour, maximum 2 hours. Okay. So after that, beyond that, if you want to, you have to pay it. This, right? So that's how some GPUs required. So you have to train hours and hours, sometimes days also, depending on the data set. Then now next step is fine tuning. So if you have a predefined model, if you want to fine tune, just now I told you, so that is bit cheaper. Then if you can use RAG, which is covered by OpenAI, where they want to give some prompt, that means there is a model. Just I want to give my prompt, like say my prompt, and I'll retrieve some data from that. Okay, that is bit easy to understand. So what is this track? Additionally, I know what is the prompt, but I need to generate the prompt. To give this particular prompt, I need data from web resources, databases, and so on. So your prompt consists of web data, database data, and so on, where you are getting the data from different sources, and then you are going to generate that prompt. So then it will respond to that prompt. That is called RAG. So this is next level, bit easy. Then prompt is the next. Straight away, you charge it for or whatever the paid edition is there, for example, you can create your PPT or whatever it is. There is a paid edition. That is a bit easy, right? Very easy. So that's okay. Now I switch, since most of you haven't gone through the transformers. So transformers, when GPT, I explain quickly. Then we'll see how you can use these generative models for cybersecurity. So this the paper was published in 2017. Okay, breakthrough in artificial intelligence domain. Why? Because all generative models are developed on top of these transformers. Okay. So anything you take, ChatGPT, BAT model, anything you take, the basics is transformers. Okay. So this is the paper. Fortunately, the first author, if you observe, who developed this model, transformer model, you see, it's a team from Google Brain. Google, so first author is, I guess, the Indian author, Ashish. Okay. The team of Google developed this. Can go through. It's a very good paper. Why it is powerful? Yeah, it can generate train on massive amount of data, as I told you, for a natural language text generation. Okay, so these are some of the parameters you can quickly go through. Why I'm saying so complex and costly? The reason is simple. GPT-4 consists of billions of parameters, built by OpenAI, funded by Microsoft, Google, Facebook, big giant in IT. Okay, this OpenAI. Then how many parameters? Just like I want to say number of parameters. GPT-2 in 2019 and GPT-3 175 billion parameters. Just imagine. Okay, which requires 350 GB. So that's why we can't run our machines. Then GPT-4 1.8 trillion parameters. And so GPT-5 we have to see. Okay. Okay, it consists of 12 layers. We'll see all layers we discuss now. And six, we have two parts, encoder and decoder. Encoder consists of 6 layers, decoder consists of 6 layers. And the key idea is it uses a concept called self-attention. What is this self-attention? So if you remember rectangular networks or LSTM, that's why to learn generative AI, the knowledge of deep learning is required. Okay, so you need to understand what are the sequence models, like RNN. So it's sequence model. If you give first word, I love cricket, I, next word love, it process like that, it's trained like that. Okay, so whereas if you see transformer, we're going to give a complete sentence, a sentences at a time, and it finds which we call it as self-attention. What is the self-attention? First word, second word, third word, fourth word, fifth word. So I have the big sentence. So no need to process word by word here. It processes all the words at a time, right? If you see the connection from first word to all the other words is like this. Similarly, this last word is also connected with all the other words. That means in self-attention, it finds the relevance. So how one word is relevant to the second word. Okay. So instead of for example, if you have lengthy sentences, if you want to process word by word, it's very difficult actually. After to remember that and classify that means for classification task or can be translation anything. It's very difficult actually. When you are translating, if I give 100 word sentence, okay, continuous sentence, so it's difficult for the decoder to translate that from English to Hindi or Hindi to English, whatever it is. So that's why this idea they come up with self-attention. How first word is relevant to second word, and it remembers only the important words in the sentence. Okay, important words. Obviously, it's a supervisory learning. So when you train with maybe at least say I can say 1 million records if you train. So obviously the weights are fixed now, the learnable parameters are fixed now, and those parameters are useful when you want to test. Okay, so for x given x, it automatically translates because it already learned in the given data. So it translates what is y. Like X language and I love cricket, what is the equivalent word in Hindi or Telugu, whatever it is. Okay, so that's what self-attention is. So we'll discuss more. I have an example next slide. See, I just want to say something. Like I have a sentence here. She saw the man with the telescope. So this sentence can be interpreted in two ways. See the first one. She saw a man who was holding the telescope. That interpretation is correct, right? This is the actual sentence. She saw the man with a telescope. This sentence is interpreted like this. She saw the man who was holding the telescope. First interpretation. Second interpretation, she used a telescope to see the sentence. This interpretation is also correct, right? Both are. Now, what is actually both interpretations are correct? How, as a human being, we are confused. How machine will understand it, and how it will understand really what is equivalent, what is the meaning for the sentence and how it can translate. Suppose if it is a machine translation task, machine want to translate this to some other language, which is confused, right? There is ambiguity. Then how? So to solve this problem, okay, not only this sentence has to understand the context. That means entire paragraph or story has to go through. It has to go through. Then this, the machine also will understand. You also will understand, right? In what context that sentence is. There is a story, 10-line story. So go through the complete story. Then what is the interpretation? Whether this one or this one. You can assess, right? Similarly, machine also using self-attention mechanism. So what are the important words in the paragraph, complete paragraph? We go through. It remember the important paragraph and context. So that's how we train initially. Then also will understand when you use new sentence automatically understand the context and translates. Okay, so this is another okay. Yeah. So this is the architecture of transformer, which so we were discussing. This is a big breakthrough in generative AI. Okay. So it has two parts actually, encoder and decoder part. So input is given here, then input embedding. Same task, cybersecurity also will discuss one research paper. So just follow, try to understand this. If you understand this concept, you can easily understand generative AI. There's nothing difficult. Deep learning, of course, throughout this architecture, if you see, everywhere they use deep learning concept. I will discuss even if you don't know. Okay. So after going back again, you just go through some textbook or resources, you will understand. Okay. So one time may be difficult, but definitely you will understand. Okay. But you must completely deep learning throughout, like whatever the recurrent neural networks they use, or LSTM followed by this is residual connection again, ResNet they use, lattice mechanism they use. Okay. This is a combination of different best works. Okay, they put up in the transformer model. Okay. So this is input embedding, actual input. Say, for example, consider this for language translation task. I'm going to use some English sentence. I need some English French or Hindi sentence. Okay, so here I'm going to use some English sentence. So I love cricket, for example. Input embeddings in NLP, natural language processing. First, it divide each sentence into words, which is again tokens. In one-hot encoding, there's a concept called one-hot encoding. Then positional encoding. So I discuss the coming slide. So more details about positional encoding. So why this positional encoding is required? Say, if I say, just now I have seen one example. When we say one word, first word is how best this particular first word is relevant to the last word, or last word relevant to the middle word, and so on. Likewise, we are testing each and every word in the sentence, how this word is relevant to all the other words in the sentence. We are checking. It's kind of parallel it happens, that's why GPU is required, frankly speaking. So GPU is required because concurrently we have a lot of words, thousands of words. Concurrently in a paragraph or sentence, I can say a story. So it has to check all the words, how this in a sentence at least, it has to find out what is the relevance. Okay. So when you are finding like saying that first word, second word, third word, fourth word, fifth word. So what is the position? So you are concurrently checking middle word with first word as well as last word also. But how would I know middle word is relevant? And this is the middle. You should know. That's why we need a positional encode. So a unique number will be given to each word to identify this is the word number. Okay. So there is a like sign and cos. There's a mathematical formula to generate that value. Okay. Actual input word, which is again converted to some one-hot encoding value, where we'll get some value of that. The same element-wise addition, like word with some positional encoding value, which is again integer value. So that's why positional encoding value with the input embedding. So that means each word has a one-hot encoding value. So add that with the positional encoding value. Then you have a multi-head attention. Okay, and then add a normalization. Then the next step, feed forward network, add a normalization. It's completely a deep learning framework. So this is for 6 times. This entire thing, this is one block actually. This is repeated for 6 times. That's why deep learning. Okay, as deep learning. So 6 times the encoded part, you're going to repeat this task. So we'll see what is multi-head attention, what is add normalization, and what is feed forward network. Again, add a normalization, and what is this residual connection that we'll see in the next slide. So just I'm discussing encoder part here. So I'll get back to you so that I'll discuss the decoder part as well. Okay. Yeah. So see this one, whatever we have. So token embedding, the input I love cricket, which we have given here, right? Then positional encoding value, I told you some integer value. Okay. Then so I'll just go explain this part as well. Yeah. So this positional encoding value they use, again, this is from some reference paper. They consider that transformer paper. Sine, this is the formula. So they come up with this 512 sequence length, then a position value, and this length, vocabulary length is 10,000, and model is 14 size and so on. They fix it and they give the reasons also why this one is. Sine and cosine, formulas they use to generate unique integer number for positional encoding. So just substitute whatever the value that we are getting, so that we get some unique values. Say, for example, I have some values here. See this one. At this point, we have different integer values we're getting. So when we substitute, see this. First dimension 0, 1, 2, 3. So anyway, I'm not going to explain complete maths here. But how these unique values are generated, see this one. Dimension 1, you have 2.5. Another 6.3. So likewise, sine and cos values, we will get unique values. What I'm trying to say is, we get unique values. Why we need unique values? I'll give this one, this value for the first one. Second value, this one. Third value, this one. Some positional value I'm going to consider for each one. So that is, they mentioned in the research paper. So this is how we have generated positional encoding values. Okay. Yeah. This one, positional encoding value, some integer value. For first word, some positional encoding value. They just wanted to generate unique value. That's all. Okay. So they quoted some research paper. They used the same technique here. Then we are getting third one. So which is similar with the second word, same third word, say then followed by self-attention mechanism. What is this self-attention mechanism? Just now theoretically we discussed. I'll show you. Okay. So positional encoding value, and then word vector, which is one hot encoder value, whatever it is for each word. They're adding this and this multi-head attention. So what is this multi-head attention? So you will have a gauge. So you are adding directly one hot encoding value with positional encoding value. Will it be disturbed? When I say one hot encoding value, some vector is there for a word, for example, it's maintained in a vector. So I'm adding some positional encoding value. Obviously, the value is disturbed. Right? Actual content is disturbed. Am I right? Right? Yeah. So for that, see this one. So these are similar words here. You can see tiger, some animals here, tiger, dog, and different animal values. Say fruits, orange, apple, and so on. Here, some vehicles called aeroplane, train, and so on. So initially, before encoding, just one hot encoding value, vector values, that is represented in two-dimensional space. Now, same thing after word embeddings with positional encoding value, just we have generated, right, using sine and cosine series. So that value is added. If you see, similar words are same, but it is big. There is a small shift in that, in this two-dimensional space, but all the relevant words are at one place, a cluster, you can say, right? So that's how this is shifted, but not all the relevant words are in the same place. We need relevant words, right? We need to understand. The machine need to understand. Okay. Okay. So now we'll see multi-head attention. So we see the encoder also we have multi-head attention. Decoder also 2 times we have multi-head attention. So I'll discuss that. Okay. So this multi-head attention looks like a small value, like small simple block, but there is a huge operation. Okay. So see this one, B, K, Q, we have different values, small calculations here, which is a linear operation. What is this different P, K, Q values? Simply, you can say, when you want to identify whether in a sentence 2 words are relevant or not, what do you do generally? So car is there, and another one is bus is there, truck is there. 3 are similar words, right? So we just want to understand. So how you can do that? Say machine, yes, as intelligent people, we can easily understand since we train that way and we can remember that. But machine won't understand, right? So using this multi-head attention, actually, there is a concept called in database also, DBMS also, you might have studied. For this query, the answer is retrieved. Something like that. For each word, different questions are asked. Okay. So, for example, I love cricket. What is I here? Is it a person name, place name, or what is it noun? And verb and so on, right? It's a key. Yes. So we are asking question, different questions, not single question. Okay. So different questions can be asked, and then what is the answer like? We return some values in that query. So query key value. So we like asked each and every word, different questions can be asked, and try to find out what is the word, and then ultimately we are going to find whether these two words are relevant. Okay, and not only these two words, Nobel with committee, committee with words, and so on. So this particular word with all the other words, how it is relevant. Similarly, optics with last word to remaining all words. So this happens concurrently, parallel. Okay, so and then it has to learn. When we say artificial intelligence, machine learning or deep learning, it has to learn from the data, right?
I have a question. So, in every statement, every word will be considered as a parameter.
It's not parameters. Okay, parameters are different. Parameters in the sense, see, when I say this is X is parameter, here, sorry, W is parameter, X is your input. Okay, so parameters are weights are, I can say, I have given some sentence. You have to understand. I'm going to go. In Telugu, it is నేను ఇంటికి వెళ్తున్నాను. So it has to understand. I have X and Y, right? You are going to give this X and Y to your model. Okay. So such sentences I'll give maybe thousands of sentences I'll give. Okay. I'll train. So if I say I, నేను, may, something like that. Okay. So machine learns from the data. Okay. Now parameters are initially randomly generated. Okay. In backpropagation, the training phase, these are adjusted so that these learnable parameters are fixed now after training process. Now, when I give you a new sentence, it has to translate. It's a machine translation task. It has to translate the given English sentence to any other language, whatever it is that you have trained your model. Okay.
So basically, it works on association. Association of the different words. Like how many times they have associated together. This count is being, it has to be taken, right? Like, let's suppose I'm using a word. You have started with I love cricket.
Okay.
So love and cricket will be associated with each other.
Okay.
Many a times, like being a youth, everyone in India says I love cricket. So love cricket is a association of two words.
Correct.
Right. Now association generally we define in parameters.
Yeah. That's what I'm discussing now. Now, so I have okay. So for word, this is my parameter. Randomly I mentioned. Now, how much data you are giving like for your model to train. So you give the data. Now these parameters, like learnable parameters, it learn from the data. Okay. So I love cricket, India, whatever it is. You give all context. Now your transformer depends upon the context. Okay, maybe next sentence is there. Next sentence is there. So when you are writing story about India, so the context is for India. So when you write story for cricket, the context is with cricket or football, whatever it is. That's how these parameters are fixed. Query, key, and using these, we are just multiplying, matrix, element-wise multiplication we are doing, and we are storing those values. And using softmax function, it's a probability game, simply. So for the given sentence, I love, is it cricket or India? Okay. So in your training data, if you train with more data with India, your probability, like your model will predict India as the next year. Understand? So if you train with some other word, obviously, cricket, obviously, it's going to predict next word as cricket. Done. So now these are X is my input taken and W is my learnable parameter. Okay. So likewise, for each and every sentence, you're feeding to your transformer and you are asking what is this, what is the relevance. So I'll go back. Previous one. Yeah. So how this is your X, right? So for this, we are asking different questions and ultimately we're finding the relevance. Okay. How you're finding the relevance, we'll see. Yeah. So query and value, it retrieves some value based on this similarity. And we are going to use some softmax function. There is a softmax function in deep learning. So it just finds the probability. Okay. Say, for example, if I see input as 313. So I love cricket, so which is translated into 110 just some imaginary values I'm giving here. The formula is e power g1 divided with sum of e power g1, g2, g3. Since I have only 3 words there. So now what I'm getting, input is something like this to the softmax layer, and output is I'm getting some probability value 0.8812. Just assume this as I love cricket. Okay. So I'm getting this is by, like I said, actually, if I say classification problem, say I'm giving some input as whether this is ransomware, some cyber security attack or not, something I just want to find out, or I want to classify. I have 5 types of attacks. 1, 2, 3, 4. What it might be. So I just want to find that. So obviously, first step. Okay, threat 1, 2, 3, 4. So for the first one, it has given high probability. Then the cyber security threat is this. Can use that way. So same thing, like with bad model, how you can do that for cyber security, we'll discuss. Okay, so this just softmax layer input is given. It finds a probability. So whatever the class highest probability is, you can say word I love. What is the next word? India. So for India, I'm getting highest probability. Then machine produces India as the next one. Okay. So that's what is given here. So there is a softmax layer. Where is that? Yeah. Multi-headed addition, and then yeah, this is my softmax layer. So query key value, these two we are considering, we are multiplying, scaling. It's nothing but in deep learning to avoid. So it has a lot of layers. Just now I have seen 6 layers, right? So with random weights and what are the given inputs, when you are multiplying random weights in input, so it will go some beyond some values. That's why to keep those values in a range, we use scale. Okay. Then softmax layer. That's how we discussed, right? Softmax layer. Then followed by this query key value with query k, that is key, with whatever the value it is generating for that word. So we are multiplying that and concatenating that, and finally which is given to a linear layer. So this is the actual procedure. So I hope this one, the linear dot product addition, concatenation, linear. So this is one thing. Then add normalization, there is a concept called skip connection. This one is the popular deep learning architecture, which is residual network. So when you have 15 layers, 20 layers, VG60, VG80, whatever it is. So input whatever the input that is given. So you are multiplying with random weights, layer by layer, you are processing it with like to improve features. So that time what will happen? Keep on multiplying with random weights and the input value, you will lose actual content. By the end of the layer, maybe last few layers, we lose the actual content. So when I have a value, I'm saying this is a cat. But what we are doing in deep learning, at each and every position, we are multiplying that with some random weights that we call it as filter. Okay, so filters are there, right? So obviously, this cat image would become something else, some noise image. Okay, so what you can do? That's why they introduced ResNet model, where each time we are also maintaining the actual input word, what input sentence, whatever we have, that is connected to the next. That means, so we keep the actual features, right, that we are feeding at the input end, one thing. Second thing, we are also processing. Both we are doing. That is what ResNet is, which we can solve that issue of losing. We call it as in deep learning literature, we call it as exploding gradients, when you keep on adding those gradients actually. So that's why this residual connection. Whatever the input content, still we are maintaining this content. We are processing here. This multi-headed is just now we discussed. Okay. Next, add a normalization. We are adding the actual content, this element-wise addition. Okay. And then normalization we are performing to make our model as stable. In machine learning or deep learning, we call it as normalization. So we'll keep all the values in a range. That's what normalization is. Then we feed forward network, then add a normalization. So we repeat this for n times. This n in the Vishwani paper, that is transformer paper, they mentioned it as 6 times. It's not fixed. You can, for specific tasks you want to design, maybe 3 may be sufficient. Okay, 4 may be sufficient. We have to test it. Okay, so next, which is given to the decoder. Say they have designed actually this one for machine translation. Now I have given some English sentence, I love cricket. Now I want to translate that to Hindi. So the decoder part, same whatever task that is performed in the encoder part, that is repeated here. We have a mask multi-headed addition, some output tokens are given here. Again, positional encoding. then added normalization, multi-head attention, then added normalization, like this is repeated 4-6 times again, and then a linear operation followed by softmax layer, finally, which finds the output probabilities for the given sentence. Okay. So fine. Yeah. So the softmax function, whatever the query values we are getting, okay, k values, okay, transpose of that. So this is what scaling. We use 1 to 10 scaling. Okay. And then finally we are getting check. Now this is for one sentence. What about if I have 100 sentences? What? Okay. So here, multi-head attention. Whatever I discussed, you just imagine for I have eight multi-head attentions. So parallelly, eight multi-head attentions work concurrently. 8. Okay, that's why we need GPU. So for generative AI, deep learning, GPU is required. The reason is parallelly we are doing this process. How this word is relevant to this understood. Okay. So Z1, one head attention. Z8, total heads are there. It is in that paper they mentioned it as 8. That's why 8 heads. Okay, so these are anyway parameters. Now we are using attention mechanism for this, and which we are currently is Q1, Q2, BI, this QI, KI, BI. Okay. So this is how we are finding the relevance for with one word to each other word in that sentence using multi-head attention. Okay. Fine. So finally we got Z0 to Z7. Total 8 hits are there. So all those values we get. Okay, in a vector. So from vector to again a tensor. Okay. Why we are using all this? Reasons I already explained in the paper again. This is from the paper, Transformers paper. So which has almost, I guess, 1 lakh citations. Okay. So they are saying you can read this sentence once. So American governments have passed new laws since 2009, making the registration or voting process more difficult. So they quoted this sentence and they try to find out the attention. Okay, how it is working with this sentence. If you see in each head like give some output, right? Word making, here the making word making. Okay, recognize its relevance with other words in different sense. Different sense. Okay, so in head 2, making recognize 2009 is its subject. In other heads, recognize making more difficult is a phrase. Okay, so like when you train with more and more sentences, obviously the context it will understand. Then you can easily predict whatever the sentence that is given based on its relevance. Okay, so that's the idea. So each head can say one thing, but using softmax we are just using the probability so that whichever is the attention mechanism that is best that it produces. Okay, so remaining layer normalization and all. So it's a common thing in deep learning where to make our model stable, we use layer wise perform normalization, which actually keep all the values in range. Okay, and yeah. So some examples I have given, which is not required. So this is the encoder part, right? So some sentence which we are giving, encoder part and the decoder part, if you observe, which translates that to, so it's a supervisory learning, right? That's why what is the start symbol and what we are giving, the equivalent English to some French is given here. Okay. So then decoder part, okay, this is X and this is Y, and it learns that, and finally it produces the equivalent. Okay. So I hope transformer is at least a bit okay. So I given like how it works, self-attention. There are different types of attention, but I'm not going in detail about those things, which is maybe not required. If it is completely AI-related one, I will have explained. So that you can see this one. This word, how relevant this word with this one, this one. Okay. So in the encoder part, it finds that. Okay. Fine. We go to bidirectional. Okay. encoder. Again, a similar concept here, bidirectional encoder representation from transformer. Again, the basis. I hope you got some idea of how transformer works. Okay. Now we'll see a bed model. It is built on top of transformers, but there is a difference. It is encoder only model. This encoder only model. Here we see the model. Actually, transformers for large language, like no translation, language translation, one language to another language. But it cannot perform other tasks. So, but BED is designed to solve those issues. Okay, we see the architecture of BED. See, this is transformer, encoder, 2, 3, and so on. So, how many we have? 1, 2, 3, and so on. 12. So, there we have 6 encoders and 6 decoders. But here, if you observe, 12 encoders only. So apart from that, there is a which is CLS, which actually maintains complete representation of the. That means it's kind of I can say cumulative thing. If I give you a sentence, so entire thing, whatever it is process that will be stored in the CLS. Okay. So first we are giving. So I love LLMs, for example, llamas. So transformer encoder, you know transformer encoder. So one encoder you take. So where we have it find out the query value. So all those things, self-attention is there. Similarly, we're repeating that for 12 times. Okay. So the architecture is this. Okay. Now, what you can do with this, what type of task you can solve. Yeah, as I told you, CLS. So this one, the input contains additional token CLS or classification token, which is used as the representation for the entire, as I told you. Okay. Okay. Now, pre-training bit. So bit which was built on top of transformers. But what is this pre-training bit? What is pre-training? Just now we discussed, right? So I have X model. Okay. So if I want to design complete X model from scratch, it is costly, time consuming, right? So what you can do, you can use a pre-trained model. Say I'll use bed and I'll update a bed with my own data by adding few layers, right? That's so bed is designed the objective, like for the entire Wikipedia data they consider to design a pre-trained model of bed. Now, so I can't use a generalized model. I have a specific task in my mind. So what I'll do, I'll fine tune the model, this bed model, with some other data which is relevant to my task. Okay, fine tune for downstream task. It can be anything. So which is relevant to this one. Now what we are going to do is security bit, which I'm going to discuss the coming slides. Security bit. So I use the same architecture, maybe with little changes. Okay, then I add some like input. My input is different. Obviously, I have to pre-process the data. Very different. Because security, what kind of files you have? Can be a CSV file or some other format, right? So for text data, I have some text file, so which consists of some billions of records. I have to pre-process that. That is tokenization is required, and so on. Some pre-processing is required. Similarly, for your task, security. So what kind of data it has? So you have to pre-process that data and update a few layers. So required, like whatever the task maybe can be like with BET, you can solve maybe classification task. Here, my classification task is to find different types of threads. Okay, before 5, 10, can be anything. So and name entity recognition and paraphrase identification. These are different tasks that can be performed with BET model. Okay, if you see architecture is same, there's no difference. Only thing it has only encoder, there's no decoder. Why? Because transformer is built for language translation. The base is for language translation. Language translation. So encoder part, whatever the input English is there. So it is trained that way. And for each word, it predicts the next word. What is I means may, for example. I love cricket. Love. So what is the next word? Like that. In the decoder part, we perform the task actually. So but here, that is designed for some other task. So I don't need decoder part here. So classification. For classification, I don't need decoder. I just train the given data classification can be anything, image classification or virus, what type of security related classification, whatever it can be. Okay, so fine. Okay, so bad. Next one is a generative model, that is decode only models. What type of model is bad? It is encode only model, right? This encoder only model, but is encoder only model, which is designed on top of transformers. Okay, now generative models like GPT-1. So GPT-1, it is decoder only model. Okay, so it has only decoder part. Then how like generative pre-trained transform? That's why this GPT is also designed on top of transformers. Okay, so how it is trained? See this one, GPT-1 is trained on a corpus of 7,000 bits. Okay, and then common prod, large data set of web pages. Okay, can we train this much data without traditional machines? No, it's not possible. It's impossible. Okay. Okay, so this is the GPT-1 architecture. Just an outline I'm giving. Why? Because it's not generative AI class, it is cyber security class. So that at least sometime we'll see that part. So see this one, transformer decoder, same thing, whatever the transformer block we have, decoder, block, first block, second block, and so on. So how many? Second 12. Okay. So how you can generate next generated block? If I give the prompt, say like I love, what is the next one? It has to predict. Or advanced versions of GPT. If I give you a prompt, it generates whatever it is. Okay. So quickly, I'll show you some prompts here. I hope at least a high level idea everybody got. Transformer, bed, and GPT. Okay. Now we'll quickly shift how to write prompts with large language models. Then next, sometime we'll see security related thing, how we can use these architectures for cybersecurity. So how many of you have used Hugging Face? Anyone? Hugging Face. How many of you heard about it? No one? Hugging Face. So please explore. So we have 8 lakhs of models. Okay. You can use it for different applications, security also. Okay. But not all models are free. Some are like paid versions you have to, but a lot of very good models which are available for free. Especially students are here. Please explore. So where you can use a existing model and you can enhance that for your specific task. So here I have used Hugging Face model. If you see, what is that transformer model? Can you read? Transformer 4.40. Transformers greater than or equal to 4.40. For my model, there are different transformers versions are available. Understand? Whatever we discuss theory, an outline of transformer. So plenty of versions are available, but for this model, at least 4.40 is required. Okay. So the model I used, you can go through this website, so which is Hugging Face website, right? So this model released by Microsoft. So 5.3 mini 4K instruct. Why I selected this one? This is a lightweight model, but very good model, where you can run it in Polab or any other platform which you can get HTTP. Okay. So you can go through this model summary. So this is a lightweight state-of-the-art open model trained with 5.3 data sets. And 2 variants are available with this, 4K and 128K. Okay. Same model I'm using here. Okay, from transformers. Okay, we are importing this auto model for casual LLM. Okay, and auto tokenizer, as I told you, whatever is given. So you have to tokenize it. So that we have a inbuilt one in Python from transformer, so which is auto tokenizer, and my model is this one. Okay, and it is required put up. You can't run this with your CPU. So this is my model. I've shown you right in the Hugging Face. I've shown you the model, and this is device is CUDA, which is required, which is available T4 in a whole app. T4 is there that you can. So CUDA it automatically comes to that T4, and then task data type is auto data type, and this should be false remote. Okay, code and so why I'm using this model for text generation? I just want to generate some text. So from transformer import pipeline. So to generate some text, so we have in generator we have a method called pipeline. You have to pass the parameters to that. So text generation, like I'm using this for text generation. That is my first parameter. Model equal to model, which I have initialized model as the previous. Yeah, what is the model? So model is auto model for casual LM dot from pre-trained model. I'm using the pre-trained model. Okay. So my model name also mentioned there as Microsoft slash 53 mini 4K instruct. So that I have mentioned here, and I'm using tokenizer, and these are default values. The maximum new tokens length, I want to generate maximum of 500 words. You can restrict it to 100, 200 also. Okay. So then I'm defining a prompt here. Okay. So messages. So in this prompt, you have to tell like the messages. What is the role? I'm the user. I have a model. I want to use that model. So role is user. Content is yeah. So what content I want to write in the prompt. So what are the roles of a faculty in the university system? So this is my own prompt. I have given something. So output equal to generated message. Generated messages, whatever that it generates from this message, that means I am the user. My content is what are the roles of a faculty in the university system. I hope it is visible, right, for everyone? You can see, right? Shall I increase that little? Yeah. So whatever it generates, my model generates, so I'm storing that in the output. Next generated text is this one I'm printing. Okay. So this is what I got. Okay. Teaching. But what is my prompt? What are the roles of a faculty in a university system? That is my prompt. Okay. I'm the user, right? I'm giving that role as user. Another role is model. Another role is model. So model by default, model is what are the model that you're using. So I have given my prompt as what are the roles of a faculty in the university system. So it is generating something like this. Teaching, research, service, mentorship, professional development, collaboration. Okay. So now you are in professional development. So I hope everybody is doing all these tasks, right? So yeah. So you can print individual tokens from the tokenizer. Say this is my prompt, right? Say something about what I have given. I think I have generated something yesterday. Oh, second one is this one. Okay. Yeah. Second prompt is say something about Malla Engineering College. Okay. So say something is positive. Okay. So I didn't say anything. So model got some data from different sources from web and all, and it has generated. Okay, you can go through. Okay, I think yesterday evening, like 8 o'clock, 9 o'clock, I run this script actually. Okay, so like this, you can generate prompts. You can restrict the maximum number of tokens, how much. Initially, this was default to 100. I changed it to 500 and I generated. Still, everything it gave 500 words also, it gave positive words only about institute. Okay, so yeah. About large language model, same thing I have used. And so what is this? This 5.3 mini, my model path is this one. So whatever I have used, so the path is given here. Okay, Hugging face. So here you have a lot of models. You just search here, whatever you want. So maybe security related also. I haven't explored why, because I'm a complete machine learning, deep learning guy. So my work is completely machine learning, deep learning. So for some applications, of course, I used to discuss with my colleagues about cyber security and other domains. Yeah, you can explore here. Again, place a lot of free models available. So reasoning also. So you see this one, LLM, I have installed the same version. Hi, my name is Srinivas. What is 1 plus 1? So I got some very good results from this. So you can define what kind of template you want from large language models. So this is prompt template. So prompt template. Yes is the start symbol. User, we are the users. Whoever is using or whoever is writing prompts. And then assistant. So where assistant is your model. Okay, this is the prompt template. So for the prompt template, you have to give the template and input prompt. Okay, so I have given some prompts here. Yeah. Okay, what is 1 plus 1? It has answered. My name is so and so, and what is 1 plus 1? And it can also remember. Okay, so yeah, see this one, LLM chain. So from long chain, I am importing LLM chain. Okay, I am defining the template. So I want to write some prompt. So what is the template of the prompt? First, you have to initialize. Okay, so however you are defining your function, right? You are defining some function, for example. So the function template, how many arguments you are passing? So what type of argument each one is, right? So data type, and what is do you have any return values to that, and so on, like that. So you can also initialize your template for the prompt. So title of the prompt equal to prompt template. I am initializing what are the template I have. I am the user and create a title for a story about summary. So whatever story you want about something. And second one, title is output key. Okay. So here I am mentioning title.invoke. There are different methods you can explore. I am just giving one, title.invoke. Summary, I have mentioned generate some title prompt with output key is title. So what is that title? I'm initializing, that is my input variable is summary. Summary is a girl that lost her mother. About this, I'm asking to generate my large language model a story. Okay, what it generated? Summary is a girl mother. Okay, so what I'm expecting for this summary, I want a title. So what it generated? It generated something. Large language model generated something. Whispers of a failure, the journey through loss. It has generated the title also for the story. Okay? Okay. So you can give different prompts like this, and you can combine all the components in a full chain like this: title, character, story, like this. Individually, you can assign, and you can ask large language models to generate. Okay? It has generated some story. Title I have given, character I have given, story I have given. So then you generate using these three. Okay, so which model we are using? What are the model? Okay, models and cyber security. Now, you got some idea about large language models like Transformer, Web, ChatGPT, basic architecture. So large language models, how can you use the cyber security? Now, you got some idea? Okay, please explore hacking phase, like Transformer models available, ChatGPT, and we have some problems like this. Where you can fine tune your models. Free models you can use, and top of that you can train. Okay, we'll see some of the, and if you have some problem, where you can fine tune your models, free models you can use, and top of that you can train. Okay, we'll see some of the applications. Can someone tell me few use cases for this cyber security? Any use case cyber security related in large language models where LLMs can be used. Any idea? Yes.
Call trackings.
Call trackings. Okay.
So basically, processes the language. What language? What encoding has been used to decode those languages into some meaningful threads.
Okay.
To get some meaningful threads.
Okay. So do you have any data sets for that? Standard data sets for that?
No.
No?
As
That is important. So when you want to use large language models for cyber security, first thing you need some standard data set. So what are the use cases to like solve this kind of issues? What are the standard data sets that are available? First thing. So you need to study, first you need to understand the problem. First thing. Second thing, what are the standard data sets are there? Okay, then try to use some existing like for example, BET is available. Okay, now first try to use this data set and run on basic BET model or any other model. Then check your results. Now how you can improve that. So that is next task. So we'll see one good example here. The automation, cyber forensics, chatbots, so penetration testing, security protocol verification, security training and awareness. So these are some of the use cases. So I can't explain all these use cases, but I'll take one use case with one large language model. So in detail how we can use that particular use case and how we can use BET model, a variant of another security BET, how we can identify these threats, security and cyber security. Okay. I want, right? So next, tokenization. And usually, whatever the text that is given, it is tokenized. So each word is a token, right? Similarly, the source code also, it has to be tokenized. So embeddings, then followed by positional. So we just discussed, right? Positional embedding. For each and every token should be assigned with a unique value, and that is identified uniquely in the given data set. Unique value. So positional. Then attention, feed forward network, attention, feed forward network. So and so on. We are repeating this several times. How many times you want to repeat? There is no standardized method. Understand? There is no standardized method. So for your problem, we don't know, right? What is the feature set? How complex the data set is. So you just try and error. First try with 5-6 basic standardized model. There is 6 encoded models. And the BET model, there is 12 times they repeat it. Maybe you can try with same and then decrease maybe number of times 10, 8, so you can do experimentation. Okay. Then finally, what we have? A softmax layer. A softmax layer, which again probability distribution function. So which finds whether it's safe. So 80% is safe, 20% is vulnerable. Obviously, it classifies this particular given input as safe. Suppose 60% for vulnerable and 40% for safe. Then obviously that is a threat. Okay. So a basic mechanism. Okay. So I consider a recent research. Why? Because if it is generative AI, I would have considered my work, but I don't work in cyber security. Okay, so I have to agree that. But a recent paper, very good paper I consider. So I cited that paper here. So see this one. They have used BET model and they're calling it as security BET. They renamed it as their own model. On top of BET, they built. Okay, that's why security BET. So just saying lightweight model. So they use a unique way, called privacy preserving pixel length encoding. So using this combination of PPFLE, this simply it's kind of so when you're giving input text and dividing that into tokens and then embedding and all they're doing, then the input data is different. Here it is language related, like text related. So there it is a different one. Data is different, right? When you are receiving from a network some network data, obviously the format is different, right? It's not text, obviously. So different one. So they're using this PPFLE combination of BBPE, which is the existing. The combination of these two they use, and they try to find out security threats using this BET model. Okay. So how many parameters? 11 million parameters they are using, and this is the algorithm. Okay. So data set, that's what I told you. What is your problem? Then for that problem, what data sets you have? That is very important, especially when you want to use AI in your security related issues. Then a feature extraction, if required, then followed by they propose this one, privacy preserving pixel length encoding. Okay. Then tokenizer, white label, BB tokenizer they're using. So these are actually plain text. If you observe, this is related to text. Since it is not text exactly text, so they want to apply this bed or transformer model for security related one. So they're doing some pre-processing. Okay. Then security bed embedding is there. Then contextual representation followed by train. So normalization, whatever we discussed, tokenization, frequency filtering, and vocabulary creation, and so on. They are doing. Okay. So fine tuning with softmax acceleration function, which is the last layer. Okay. So please. So I think with this you'll understand. What is this? What is the input? So original network traffic data is the input. Okay. For the actual bed, it is just text only, right? So input is different. So for this, to process this input, obviously, you have to pre-process three. That's one. So feature extraction and these tasks. So see this one, after extracting the features using a PPFLE method, so privacy preserving. So this is some ransomware and this is normal and so. Okay, that's CSV file. So after pre-processing, so we have this kind of this is a feature. Then what is the category? What is the class? So class is type of cyber security, like cyber threat, right? Then so text data input. Then byte level encoders. If you observe, the sequence is similar to the byte only. So here we have only is it encoder type or decoder only mode? Encoder only mode, right? Right. So then tokenizer the traffic, tokenize traffic data followed by byte embedding. So byte encoder. So since it is encoder only model and contextual representation, finally softmax layer. Say softmax layer which predicts DDoS or DDoS, UDP, DDoS, ICMP, and so on. Are none. So different classes are there in the data set. So like using security band model is able to classify what type of virus cyber security threat it is. Okay. So data set, this research paper they consider exclusive for IoT and industrial IoT connectivity protocols related data set. So it consists of this type of threads, 5 threads. One is DOS or DDoS attacks, information gathering, and MITM injection attacks, malware attacks. So I have given a description about all these attacks. What is that attack? I think I have a diagram as well. So HIIoT data set. This one you can just Google it, you'll get. So how you can use this for some other problems. Okay. So DOS or DDoS, it has TCP, SYN, port flag, UDP flag, HTTP flag, and so on. Similarly, information gathering, port scanning, and OS fingerprinting, and so on, vendor scanning, and so on. So malware attacks like backdoor attack, password cracking, and so on. Password attack. Okay, so like this. So an injection attacks also accesses SQL injection, uploading attack, and so on. So these are different. Majorly, they are categorizing into 5 threads. Each thread again consists of these subcategories. So this data set description, as I told you, you need to understand problem followed by what are the data sets that are available. So that also you have to explain. Okay. So feature extraction, as I told you, they are using a different approach. Like after feature extraction, they got like something like this, 15 features. First 15, of course, it has 61 features total. Okay, using the PCAM files. So first one, this is the first feature, which is a frame and the date and time. So some kind of features they extracted. Then this is complete wet model. How they have utilized this. So high level workflow of a security wet model. Same thing, input we are giving. So encoding, then repeat it for several times. Okay, and bed intermittent representation. We're repeating this for several times, right? Bed self-attention, first time, second time, then the intermittent representation, whatever we have, then the output pooling layer. So then the final output. So whatever we have discussed, if you see a dense layer, activation layer, everything is there. So query, what is the query? For your data set, query, key, value, and dropout layer. So dropout, I think I haven't discussed. That is very basic operation in deep learning. So when you have huge amount of data, when you are training it regressively, so it may lead to overfitting. Okay, to avoid that, there is a concept called dropout. So where some of the layers, the deep learning, 50%, 30% of layers are dropped. Okay, so that will stabilize them. Okay, that is called dropout concept. So they use a dropout. So no need to go exactly the same architecture. You can customize the architecture as per your requirement and your problem and your data set. How many features are there? How many examples are there? Okay. So distribution of data across 14 attack types. Just now we have seen the data set description, right? So here attack type is given, number of samples available. So if you observe fingerprinting related, you have only 1,000. Is it a balanced data set? No, right? It's not balanced. Balanced means all classes will be equal. So first class, I have 1,000 examples. Second, grade, I should have 1,000 and so on. Okay, but here now you need to think about. So here I have DDoS something 50,000. DDoS HTTP TCP 50,000. These are okay, but you see bottom side 1,200. Okay. So MITM we have only 1,200. Fingerprinting 1,000. XSS 10,000. So imbalanced data. So what will happen if you go ahead with the same examples? So I'm training 10,000. Total I have 10,000 training samples. Out of 10,000, 1,000 are one class. Remaining 9,000 are other class. What will happen if you train 10,000 examples with that? 1,000, 9,000. It is biased towards more number of examples. Your model obviously is trained towards more number of examples. That is biased towards more number of examples. That should be avoided, right? So for that, there are different ways actually in deep learning that you can study. Where somewhere, so you can try to balance the data, then go with a different approach maybe. Okay, so they got some results. Same paper which I quoted in the first line. Some they with bed model earlier 0.984 is the highest one. They got almost 14%. Huge jump. Okay. Some like in research point of view, where you can plot accuracy and loss functions here. So left hand side, just I guess the number of epochs are very less, 3 or 4. Still they got better results. This see this train and test graphs, which is almost nearby. If these two are like this, for example, your test accuracy is low, your train accuracy is high. Then what is the issue? So let us say your the train accuracy is very good, it's 98, but test accuracy is here somewhere here. Not even 0.94, somewhere 40, 50.
It's overfitting.
Overfitting. So, like, how we can solve that? What are the reasons and all? We have to study. Okay. Some confusion matrix. These are all you can plot, and the real time experimental setup also they have shown. So internal network, data collection, and then followed by feature extraction, which we discussed. So they use this PPFLE as encoding as that, and then classification, which is security bit. So it is classifying either. So just this is kind of recent book where you can explore. Someone is interested to research in this. So LLM based solutions for cyber security. Most of the papers are 21, 22, 23, 24. So very few papers are old. They also use, I have just gone through 17, 18 and all, whatever they they're done. That is related to LSTM, RNN they use. That is now outdated. Where you can go with new LLM based methods. So see this one. This is 24, 24, 24, 24. This side, phishing and spam detection. So all are 24 papers. These are works. Okay, then hardware security bugs. Again, 23, 24 only. So very simple. Large language models they're using in cyber security. So like all the papers, I have few more. Okay. So 23, 24 only. There's a huge scope for of research in this area where cyber security related problems you can use, you can apply large language models. Okay. So malware classification, cloud threat forensics, and digital detection. Okay. So what models actually you can use? So I have that in the next time. See this. This is simple literature survey where someone is interested. I can see GPT-3 also. You see GPT-3. Just now we discussed decode only model, right? GPT is decode only, and this model anyway GPT-3 is the best model. So parameters, how many parameters? 175 billion parameters. Straight away we can't run that. What we can do? Use that GPT model, pre-trained model. Just add something. Okay, maybe GPT may be difficult for our research. Maybe it's very huge. See, 300 billion. See this, 1,000 billion. I don't know what is this. T5 model, encoder, decoder, both are there. Okay, bad model, which we discussed, 250 billion. Training tokens on parameters, 340 billion. So, what kind of use cases are there related to cyber security? So, malware detection, threat intelligence, social engineering detection, and so on. So, most right? Just go through this. So key training techniques also you can see. Yeah. So whatever we discussed, back propagation and gradient descent, those are very old models where you can see is masked LM. Okay. So pre-training in context learning. So straight away we can't take can't train any GPT-3 from scratch. So pre-training model they have used. Right? Again, pre-training mode. And here, for this, encoder, decoder T5, pre-training and fine-tuning also So mostly, either you have to use pre-training with fine-tuning only, most of the cases in our research. Why? Because we can't train from scratch. Okay? So all pre-training models. A few more models, lightweight models. Pet related, yeah, even I have gone through, which is related to generative AI, it's not with cyber security. I have gone through Robert TA, so which is better version than BET. Base version is BET, and they have updated it. There are some drawbacks with BET, so they came up with Robert TA, B, different versions are there. So Excelite and Prophet Net, Falcon. So these are few models available. Okay, as I told you, in hacking phase, we have 8 lakh models. So out of them, 3 models are there. So why don't you go through those models? For security related, which one is working better? Go through, find out the data sets. Okay, first run with the existing data sets, then try to fine tune your data sets with the model. Yes, so that's a
Data sets will also be available in
free. So whatever I told you, this research paper I explained, so it's free. Okay, okay, so I'll stop here. Yeah, if you have any questions, please. Okay. So thank you. Hope the session is useful.
I would like to express my sincere thanks to our chief guest, Dr. Srinivas Vatila sir, for gracing this event with his presence and sharing invaluable insights. Your words have truly inspired us and set the tone for the program. Thank you so much, sir.
So there is a lunch break from 1 to 2. And in the afternoon session, we have related to firewalls. And the team from JP Morgan is here already. So after lunch, the session will be started at 2 o'clock. From industry session this one, they are more related to firewalls and threat mitigation, how they are secure.